Assalamu alaikum, dear students. We're back with another video lesson. In today's video lesson, we're going to start a new concept. So we're going to talk about the properties of waves here. The first thing to begin with, we're going to talk about wave motion here. What is wave motion? Now, you might have experienced this. Let's say there is a pond of water, okay, and you throw a pebble, small rock or stone, into the surface of the water here. Now, before throwing this one, you can see that the surface of the water is calm. But then after you throw the pebble into the water, of course, there will be disturbance, right? So what do I mean by disturbance? And this rock is, or small pebble, or the pebble here, it is going to disturb the particles here, where the particles are going to move now, right, or vibrate in here. So we'll say they are disturbed now because they're not in rest anymore here. So this disturbance, of course, produce ripples, you can say, and these ripples would spread across the surface of the pond, and which is in a circle. You can see that, which is away. They're moving away from the surface of the water. Okay, in a circle. Don't forget this. Okay, now, but if we examine the motion of the water molecules exactly, what does it look like? Now, before we throw the pebble, you can see that the surface of water was calm, the surface of the pond. But after you throw the pebble, you can see that for part or some part of the water molecules, of course, now they're going to move up and some other parts are going to move down. Okay, in other words, now the particles are not in rest anymore here, so these are disturbed. So some particles or molecules will move up, some others move down, and this is how a water wave look like at this point right here. So because they were at rest, so now they're vibrating, and you can see that these vibrations are perpendicular to the direction of wave travel. So these molecules are no longer in rest. So we'll say the surface of the water is disturbed. Now, this is the motion of a wave. You can see that the wave is moving in this direction. That would be the direction of the wave, while the molecules would be just moving up and down. For some other waves could be moving back and forth, which is parallel to the direction of the wave, which we're going to discuss later for that one here. Okay, so this is exactly what happens now. Now, there's one more thing you need to know. Once these waves are moving here, and by the way, waves are transferring energy here. So as the wave is traveling or passing through the surface of the water, it is just transferring the energy, let's say, from one part of the water to another. But the water molecules, remember, or the particles of a medium, whenever a wave is passing through a medium, okay, and we'll talk about what is a medium as well. Once a wave is passing through a medium, the particles of the medium remain at the same place. The only thing that they can do, they might vibrate or move up or down, vibrate up or down, or maybe move back and forth. But the net displacement, or how much they go, the total displacement they travel here, or the net displacement, it is going to be zero. In simple words, we can say these particles are not changing or leaving their position. After all, they'll always get back to the same position there. So the bottom line of this, the wave is moving forward while the particle, it is just vibrating in their locations here. That'll be regarding the wave. So don't forget, then this is what you see for a child in playing with the football. Maybe the football landed on water and then you were throwing, let's say, stones or pebbles at the football, hoping that maybe this one would displace the football, but it was very difficult and it was not. In that case, of course, if there's a piece of wood or something, maybe a leaf that is on the surface of a pond, it might just bob up or down or move up and down while the water waves are moving forward here. So what does this tell you? Once again, this would tell you that if there is an object or something on the surface of the water just moves up and down, that would be the same as the motion of the particle. The particles are not moving, it is only vibrating at their location. But what is moving is, we can say, the disturbance, the energy, or the wave, we can say. Okay, now let's get back to this one. So this is exactly what this part is about. It says, consider what happened to the surface of the water when you drop a pebble. And of course, the disturbance created by the pebble generate water waves, and these water waves will spread and move away from the center of the disturbance. And if you examine the motion of a leaf, a football, a piece of wood on the surface of water, you would notice that that thing, whatever that is on the surface of water, it will only move up and down, back, or could be some back and forth further things about their original position without moving further or away from that location here. So this object, a leaf in this case here, does not undergo any net displacement from the motion of, or you can say net displacement from the motion of the wave. Yani the wave can travel, but the object or the leaf that is on the surface of water will essentially remain at one place in here. And then the water waves move from one place to another, but remember the particles or the molecules of the medium, which is in this case the medium would be the water, do not move agad, they only vibrate. The next thing that we have says a wave is the motion of a disturbance here. Now remember this, especially whether if it is sound wave or water wave, if you want to create a wave, you need a source, right? And then this source, of course, cannot create a wave without a disturbance. So for example, now later on, we're going to study perhaps for sound most, later. Now, if you want to create a sound, let's say you'll have to have something so that, let's say you hit a desk, all right? You just tap on the surface of something. Tapping the surface of something produces a sound. For example, maybe this board right here, yeah? So this tapping, it makes the surface of this, for example, smartboard, this board vibrate, and this vibration produces a sound. So we can say that without the source that disturbs the surface or the medium, there will be no sound or no wave at that point here. So once again, ripples in a pond start with a disturbance at some point in water. These disturbances, of course, cause the water on the surface near, for example, that point to move, of course, and then which causes other points or other molecules to move with it. This is how the wave will be transferred, giving the energy from one molecule to another, and then this molecule, of course, go back to its location, and then now this one will give it to the next. So this is how the energy of a wave will be transferred from one point to another in a given medium, we can say. But don't forget, we said the energy of a wave, or the wave can travel, which is the disturbance or the energy of a wave can be transferred from one point to another, but the particles of the medium will not change their place, or you can say they do not move in general. So how can we define the wave in this case? We can say waves are the motion of a disturbance. That is as simple as that. Waves are the motion of a disturbance. Now the next definition is that we have is we can say the medium. What is a medium, Baba? Medium is anything that allows the wave to pass through. So we can say it is the physical environment that the wave is, or the disturbance are passing through. Okay, that would be the definition of a medium. Once again, it is the physical environment through which the disturbance can travel through. That would be the wave in here. Now, regarding waves, there are two types of waves that we're studying. Right? Remember this. One of them is mechanical wave, and the other one is electromagnetic waves. And you need to know the difference between these two, because the difference is important. The first thing that we have, we can say it is a mechanical wave. Okay, so let's just make a table, or remake this table right here. Now, when it comes to waves, there are two types, don't forget. Okay, so waves are two types. One of them, that is mechanical, and the other one is non-mechanical. All right, so once again, the first one, mechanical. When we say mechanical waves, of course, these are the type of waves that they need a medium, right? They need a medium to travel through. They need a medium to travel through the medium. If there's no medium, this or these kind of waves cannot travel through. Well, then the second type of wave that we have, it is, you can say electromagnetic. That would be non-mechanical at this point here, which we can say electromagnetic electromagnetic waves. These electromagnetic waves, they do not, they do not need a medium. They do not need a medium. Okay, now remember this, the two types of waves are mechanical and electromagnetic. Some of the times you can call them non-mechanical too, by the way. All right, so mechanical are those waves that need a medium, electromagnetic, they don't need a medium. Now, mechanical, of course, device to two types in this case here, right? One of them, it is called longitudinal wave, longitudinal waves, okay? And then, by the way, these are both, and then the other type is transverse waves. Basha? These are, remember, need a medium to travel through. And one example for each we can say longitudinal would be sound waves, okay? And then an example for transverse wave, that is mechanical, we can say water waves. Right, just like the example that we were saying, Basha, sound waves and water waves too. What about electromagnetic? Remember, the type of electromagnetics are only can be transverse wave, Basha. Electromagnetic, right, or only transverse waves, which they don't need a medium. Masha? All right, so now remember waves are, it can be divided to two categories, mechanical and electromagnetic. Mechanical waves, they do need a medium to travel through, so they need a particle, they need medium, while electromagnetic waves, they don't need a medium to travel through. And this one, we said mechanical, that would be divides to, or there are two categories, longitudinal like sound waves or transverse wave like water waves here. But electromagnetic waves are only transverse waves. And an example we can say electromagnetic waves, Basha. Electromagnetic waves like what? Like we can say radio waves, microwaves, and all that. And so now let's just write these examples and all of them. And it's best to memorize them in order too, because you need them, of course, if not in here in chapter 7 as well. So it's best to memorize them, but it needs to be memorized in order as well. So the first type that, like electromagnetic waves, Basha, electromagnetic, by the way, sometimes we just write EM, that is electromagnetic, that'll be waves in here. The types of electromagnetic waves that we have, the first one is radio, Basha. The second one is going to be radio waves, microwaves, Basha. And the third one is going to be infrared, right? And then the fourth one, it is visible, right? Now the fifth one, it is UV, we call it ultraviolet. Ultraviolet. And then that was number 5, okay? Number 6 is going to be X-ray. And number 7, it is going to be gamma rays, or gamma ray. So, see, we have 7 type of waves, and of course, I wrote it on a purpose like this one here. So there's visible wave, the one that we see it is right in the middle. So there's 3 ahead and 3 after. So radio, micro, infrared, and then visible, then there is ultraviolet, X-ray, and gamma ray. So these are all the types of electromagnetic waves that we have. Remember, each one of these electromagnetic waves, they do not need a medium, and each or all of these are transverse waves in there. But sound waves and water waves, like we've mentioned, these are mechanical waves, and they do need a medium to travel. Imagine or consider if there's no water molecules, can a water wave exist in the first place? The answer is no. So this is how crucial the particles of a medium are for mechanical waves right there. Okay, so there was one thing I forgot to mention actually. So what is the difference between the shape of these kind of waves right here? Now, regarding the longitudinal wave, if I want to draw something, it could be using a spring, it could be using sound wave and all that. Let's use a spring to demonstrate longitudinal wave. Imagine if you have a spring, at some regions the spring coil up, and some other regions the spring is stretch. And once again, coil up together, and then stretch again here. So if we take the motion of one particle here, this is how the wave or the direction of wave travel. Basha, if you take the motion of one particle, you can see that at some point it is pinched together, coiled up, close together, Basha, compressed, and some other point these are far from one another. It's the same as if it is stretch, we can say. So these particles here would only vibrate back and forth, which is parallel to the direction of wave motion here. These kind of waves are called longitudinal wave, and that is longitudinal. We could use the water, let's say the air particles, to demonstrate that as well. So if you use air particles, you can see that in some region, the air particles are very close to one another. Basha, and some other regions, you can see that the air particles are far from one another. Then another region where the air particles are again very close to one another. And then once again, there are other regions where the air particles are far from one another. So these regions here for air particle, we can call them compression, and then this will be rarefaction, or if it is a spring, we call it stretch. We'll dive into the details later, but this would be the shape of a longitudinal wave, or this is how it looks like. What about transverse wave? If we have a transverse wave, it is like a water wave in here. So this is how it looks like, Basha. So here, the particles, you can see that they move up or down, which is at right angle to the direction of wave travel here. See, these particles, if we just draw this one here, these particles can move up or down. At either cases, these are both at right angle to the direction of what? To the direction of wave travel. So this will be the particle. So the angle between this and this is 90. That'll be the diagram for a transverse wave. There's no difference between the diagram of this transverse wave that is mechanical or this transverse wave that is electromagnetic. In each one of these cases, you can see that here, even though we don't have a particle, by the way, but there will be electric and magnetic field that these are at right angle to one another. That is nothing for you to worry about. Just remember, once we have a transverse wave, the particle moves up and down, which is at right angle to the direction of wave travel. But later, the particles are parallel to the direction of wave travel. All right, so these are all that we can say regarding or about the waves right here. Okay. So one more time. Okay, so that'll be this. Don't forget that, Basha. And by the way, I've just learned something really new. If you want to know, like if you want to have this diagram without writing anything, you could just, for example, pause the video, scan this code, and then it gives you exactly what is just written right here. Okay. All right, now moving on to the next one. So what is the next thing? We're going to talk about the two types of waves one more time, but more likely, by the way, so this is what we said. There are two types of wave, mechanical and electromagnetic. Mechanical becomes longitudinal and transverse. Longitudinal like sound, transverse wave like water waves, while electromagnetic are only transverse waves. And like we said, electromagnetic waves like radio, micro, infrared, and all the other waves there. Okay, but don't forget, this is the diagram for longitudinal, and this diagram would be for transverse wave, whether it is this or that. It makes no difference in terms of the diagram here. Okay, one more time. Gutman, what are mechanical waves? Mechanical energy, mechanical waves, Sibun Baba. Gutman, these are waves that need the medium so that they can travel through. Without a medium, they cannot travel through. So remember the keyword. Mechanical waves are those waves that need a medium, Basha. So the keyword is for mechanical wave, they need a medium to travel through, like what? Like sound waves. On the other hand, or you can say, now next we have electromagnetic waves. Remember, they do not need a medium to travel through. Like what? Like radio waves. And we said, these are the 7 types of waves that you need to memorize. The first one is radio. The second is micro. The third one is infrared. The fourth one is visible. And then we have ultraviolet, X-ray, and gamma rays as well. So don't forget these, Basha. Now, one of the simplest ways to demonstrate a wave motion, how can we demonstrate the motion of a wave? Now that is also something interesting. Imagine there is a rope in your hand, Basha. So what exactly happens once you move this rope up and down here? Basha, for example, we have a rope that is, you can see that tut at one end, or you can say fixed at one end. So, and this is, let's say, your hand. And here, I'm not very good really at drawing here. So now, what do you think will happen if you just move this rope one time, just up, okay, and then back to the same place, all right? So once you do that, watch this. So just for example, let's just bring this one down a little bit. Imagine this is the wave in my hand. If I just move this one up and down, back to the same point, by the way. So there's going to be a wave that is traveling, not a wave actually, my bad. It is a pulse that is traveling through, or you can say on this rope, on this pulse, of course, it is going to move until it reaches the end. Right? What happened later? That'll be for later. But just remember, just by moving the rope up and down here, like up and back to this place, there will be a pulse that is moving on this rope here. Now you might wonder, what happened if I move the rope like after back to this place, now move down and then back up to the same point here? So almost like move up and then back to this place, now move down and then back to the same place. In that case, of course, it is going to generate one full wave this time. That'll be one pulse up and one pulse down, and you can call this one a full wave, right? So if you keep moving this one both up and down here, so there is going to be what? Pulses, or pulses would be what? Or more pulses is going to be moving on this rope right in here. So, but if we go back to the pulse thing here, if we just do that up and down here, okay, if back to the same point, good man, one pulse will be moving, yeah? So what happens if you keep doing that, for example, just up and back to the same point, so there will be more and more pulses, right? And if we have like these pulses are repeated in here. So if these pulses are repeated, what do we call this one? Do we call it periodic? Do you remember the periodic waves, or something that is called periodic, yeah? It is the motion of something that keeps repeating at a regular time interval. So if we keep, for example, making pulses, you can call these pulses periodic pulses in here. Or this thing here, it is going to be periodic, but if it is a full wave, then you can get a periodic wave. That is also true. All right, so that'll be the how we can wave, or how we can generate a wave, Basha. So if you continue to generate pulses, these pulses form what is called the periodic pulse. Now we have two definitions here, by the way. Don't forget this. A wave that consists, maybe perhaps here or there in the definition, a wave that consists of a single traveling pulse. Remember, a single traveling pulse, it is called what? It is called the pulse wave, okay? So like we said, if we have a rope, we just, for example, move that up and then back to the same point, not down, so there would be a pulse. So now, but there's only one pulse on this rope, right? So now we can call this one a pulse wave, a wave that consists of a single pulse there. So once again, a pulse, that'd be a single disturbance in a medium, or you can say it is a wave that consists of a single disturbance traveling in a medium. That'll be a pulse wave. This pulse, of course, could be using a rope, could be using a string, it doesn't matter. Okay, now the next thing that we have says sine waves describe particles vibrating with a simple harmonic motion here. What exactly do you mean by this now? Remember, we said that if we're going to, for example, you can consider the motion of the water molecule that we just went through, yeah? And we also said that a wave whose source is vibrating with simple harmonic motion, we can call that sine wave in here. What exactly do you mean by this? Now, do you remember now this is the rope one more time here, and this is one end of the rope. If we're going just to move up and then back to the same point and then move down and then back to the same point, so you're going to generate one full wave, right? And then if you keep repeating that, of course, more and more waves will follow. So that is going to be a periodic wave now, not just a pulse, it is a full wave in now. But watch this. If you're going to move your hand up and down, and then perhaps maybe up, let's say down and up back again, isn't that simple harmonic motion? Yes, it is. Do you remember what was simple harmonic motion? Good man, in simple harmonic motion, there were three conditions, right? The first condition, good man, the force must be directly proportional to the displacement. Ibasha, isn't that the case? We can say the larger the force you apply up or down here, isn't that like the particles of a medium, which is the rope in this case, doesn't it go further? In this distance, you can say, or displacement of a particle, it is going to go larger and larger and larger. So the more you move your hand up, of course, the larger the pulse is going to become here. So this is the first condition of a periodic motion, of a simple harmonic motion. But the second condition, if you remember, it must be vibrating about equilibrium, Basha, or the vibration, it must be about the equilibrium. What is the equilibrium? We can say the rest position here. This vibration here, for example, once you move it up and down and then back to the same point, as in the vibration would be about this point right here. Because if we take one particle here, Baba, this particle, it is going to move up, and then after that back to the equilibrium, move down, back to the equilibrium. So this vibration, it is about the equilibrium right here, and that would be the second condition of simple harmonic motion, we can say. All right, what about the third condition? Do you remember what it was? We said the motion must be on a straight line. When this particle is moving up or down, isn't it moving in a straight line here? Later on, you will see that it might move forward or backward, but even if it is moving forward or backward, that would be for longitudinal. That is also motion in a straight line too. So that would be the third condition, Masha, motion in a straight line. Masha, that would be the third condition of simple harmonic motion. We can say whenever there is a wave, the particles of the wave or the particles in a wave will always be moving in a simple harmonic motion here. And you do know that simple harmonic motion waves can always be considered or represented as this sine wave here. Basha? Okay, so once again, you could draw a sine wave for this one here. Basha? Sine wave would be representing the motion of this would represent the motion of this wave right here. Or you can say the particles of the motion, the particles of this wave right here. So we have another example. There is this thing that causes, instead of you using your hand to move the rope up and down here, there is this generator that generates vibration, for example, so it just moves the rope up and down here. But if we examine the motion of one particle, how does it look like? If we take the motion of this particle that is at an equilibrium, we can say, now you can see that this wave, it is going to pass through this one. So the next thing that this particle is about to move, it is going to move upward, right? And that is exactly what you see. That is A, that is what you see in B. So after the particle has moved up, now after that, for example, after it is moved up, it is going to move down, right? Because we said that if it is simple harmonic motion, it is going to move up and then back down, and then after that below there, and then back to the same point. But I don't want to draw these lines right on one another because I need you to see the difference or what exactly happens. First it goes up. Now after it is here, it is going to move down. What is the next thing that is going to happen now? This wave is passing, so the next thing is this particle that is going to move down, as you can see here. So, but before that, it has to get back to the same point, like the equilibrium position. And then after that, it is about to move downward. Then after, for example, moving downward, it is going back to the equilibrium position, and that'll be right going back to this thing. So this is what happens in one full cycle. The particle would move up, and back to the equilibrium, move to the bottom of the wave, and then back to the equilibrium. So this is how it is going to repeat. But I hope you notice this one. If you look at, for example, the motion of this particle here, it is always vibrating in a straight line while the wave is passing. So the wave would be passing, but the particle is not changing place, or it is not moving with the wave. The only thing that is moving is the wave, and it is energy, we can say. And this, of course, represents, or it is the same as a sine wave, we can say. Basha? How does a single point on a string move as a transverse? As a transverse wave passes horizontally by that point. This is a point here. If a wave is passing, okay, here's a transverse wave. When you can start at this point or at any other point, doesn't matter. But consider that this wave is moving now, Basha. The point is, it can only vibrate up or down at its location. So as the wave passes, for example, we can move, let's see if we could do that here. Actually, not here. Let's use the other one. See if we can use or demonstrate something similar to this, perhaps by using the this. Okay, actually this one. So we can say we have a particle. This particle is right here. I think I should have drawn this one a little bit lower. Let's make this one lower. So here's a particle, and now there is a wave that is about to pass through there is a wave that is about to pass through this point. What do you think will happen as this wave is going to pass through this one here? Now we can see that the first thing that, normally a wave would be starting at this point here, right? Doesn't matter which way it is going to move up or down here. But according to this diagram that you'll see that the first thing that it will happen now as the wave is passing, imagine that this is the slide, the particle is just getting on the slide but the slide is moving beneath the particle. So the particle, it is going to move, of course, downward here, right? So it's going to be right at this point. And then after that, well, for example, now this is how it is going to, the particle is going to be right at this point. So now it is going to move down. After the wave is passing, you can see that, for example, this particle is now going to move back up to the same point that it was. So let's erase this now. Right, this particle, that was too much. This particle, it is going to move back to the same point. So remember, it was at this point, now it is going back to the same point. What do you think as the wave is passing through? Now imagine it is a person that is riding a roller coaster now while the wave is passing through. I wish we could use something like an animation here. So this particle will be riding or getting on this wave in here. So first that is going to move down here while the wave is moving, and then it is going to climb up in here, and then the next thing it is here, then the next thing it is going to be right at this point, and then after the wave is passing, it is going to get down here. So this is how it is going to be based on this diagram. First the wave is going to, or the particle is here, it is going to, that is first, that is going to move down, that'll be second, and then after that it is going to get back to the same displacement, or that'll be equilibrium, let's say, and then after that it is going to become, or go to the top, that is 1, 2, 3 would be 4, and then after that is going to get back to the same point. That is what happened in one full wave or cycle, you can say, Basha. So the particle, or what happens to the particle, Baba, the particle only vibrates up or down, which is at a right angle to the direction of wave travel, but that is only in transverse, don't forget. All right. Not this. All right. So going back to this, Baba, says, how does a single point on a string move as a transverse wave passes? Good man, a single point, the particle moves up and down, which is at a right angle to the direction of wave travel. This is the direction of wave travel. Okay, but the particle here, it only moves up and down, which is at a right angle to the direction of wave travel, and that'll be the answer to this question. All right, now let's talk about transverse waves now, like a little bit in details than what we were just explaining here. The first thing that we have, Abba, remember the definition of transverse. It's been in Uzari many times as well. We can say transverse waves are those waves, Basha, that do not need a medium. And what is the key? Remember to, it could be, forget what I just said. So we can say transverse waves are those waves where the particle vibrate at a right angle to the direction of wave travel. Basha? So that is the key for transverse waves in there. So we can say it is a wave whose particle vibrate perpendicular at a right angle to the direction of wave travel. Don't forget. Okay, so we can say in transverse wave, like one more time, the particles of, let's say, the medium would vibrate at a right angle to the direction of wave travel. But the second thing is, remember, we can say most of, we can say that electromagnetic waves that are transverse waves, they don't need a medium. Basha? Or in other words, we can say that most of the transverse waves do not need a medium. Basha? And don't forget, all electromagnetic waves are transverse waves that do not need a medium. But we cannot say all transverse waves do not need a medium. We cannot say that. Okay, so now a little bit more regarding transverse wave is this diagram. So let's make this diagram one more time in here. So here's, we have a transverse wave, Basha. Let's draw this one perhaps. Okay, now we have a transverse wave. Let's maybe changing color here. This is a transverse wave. Masha? No, actually, let's just make more. I don't know why. All right, let's make more. So here would be a horizontal line, and now we have a transverse wave. And of course, you can continue with more if you want to. All right, this is how a transverse wave look like, by the way. Okay, it could be a water wave, could be whatever that, like that looks like this if you've seen. All right, so what are the parts? Now, this is called transverse wave, Basha. Now, there are some things you need to know regarding the transverse wave. We can see that the highest point in a transverse wave, it is called crest. I'll repeat. What is the highest point in a transverse wave called? Crest. So this is a crest, and so does this, right? All right, what about the lowest point in a transverse wave called? It is called trough. What is it called? Trough. So now crest is the highest point, trough would be the lowest point. All right, now we have a few more things. The displacement or maximum displacement from the equilibrium position, that is called what? That is called amplitude. Okay, so what is amplitude? It is the maximum displacement from the rest position or equilibrium position. By the way, this is also a displacement here. This is also another displacement. You can call it, for example, A, B, C, it doesn't matter. But which one of these is, let's just call them number 1, 2, and 3. But which one of them is or has maximum displacement? That'll be this, right? So only this one can be called amplitude, not these, right? Don't forget, when we say amplitude, it is the maximum displacement, right, from the equilibrium position here. So that'll be maximum displacement. All right, the next thing that we have, that is the wavelength, Basha. So what is the wavelength in here? We can see that, or we can say the wavelength, that'll be the distance between two adjacent similar points in here, Basha, or the distance between two adjacent similar points, that is called a wavelength, Basha. Let's not forget here, we'll use the letter A for amplitude here. For the wavelength, we'll use the symbol lambda, which is a Greek letter, Basha Baba. Lambda, it is a Greek letter. It is a Greek letter that is used to represent the length of a wave. So this we call what? We call this one wavelength. And what is the length of a full wave here? Regarding this one, this is the easiest. Perhaps let's draw this one more time. If I have a wave here, doesn't matter how many or how much it extends in here, the distance from one point on a wave to the same exact point on the wave, that is one full wavelength, don't forget. So you could start from crest to crest, you could start from trough to trough, doesn't matter. You could start from this point here, but if you're going to start from this point, you really have to be careful. Is this the next point on a wave? The answer is no. How do I know? Because later, the wave is about to go up, right? At this point, the wave is going down. And the condition for wavelength, it has to be the same exact point on the next wave. Later, it is going up. Here, it is going down. So do you think it is the exact same point on the next wave? No. So just keep going here. This point right here, because at this point, the wave is going up again. So we can say the distance from this point here all the way to this, that is going to be one full wavelength. We will only choose one of these. Like, we don't have to choose all this together. You're either going to choose from crest to crest, trough to trough, or from this to any other point. Yani. You cannot say how many, for example, these are whatever. So wavelength would be no matter which or where you start measuring the wavelength, each one of these is going to give you the same number. So that would be the wavelength of this wave. Yalla Baba, let's do or summarize this one more time here. Once we have a wave, okay, we said, what do we call the highest point? We call it crest. This one in Uzari, Basha. So what do we call the lowest point? We call it trough. What do we call the maximum displacement from the rest position or from the equilibrium? That is the amplitude here. And the distance between two adjacent similar points on a wave that have, let's say, for example, the same speed and direction, that'll be one wavelength. So it doesn't matter where. One more time. Crest, that'll be trough. Okay, this is the amplitude, and we can say this is the wavelength. They might make, for example, this. By the way, they might make this one A, and this one B, perhaps, and then this one C, and then perhaps maybe something else. they might tell you something, we're starting here, perhaps maybe something like this, starting from this all the way to this end here. Maybe they'll make this one D here. So, if that is the case, which one represents the wavelength? That would be A. Which one represents the trough? That would be C. Which one represents the amplitude? Remember, we have, so this is, let's erase this one so that you can see this perhaps maybe better. Masha? So would this be the amplitude, by the way, starting from the top to the bottom? The answer is no, because the amplitude, it is only from rest position, either up or down. We cannot take the whole thing and say this is the amplitude. So agadlebi, this is not the amplitude. Only this part would be the amplitude here. Only up or only down. We cannot consider this as a whole. So now one more question perhaps. Later, we have a question later, you'll see that. It, of course, starts with a wave like this. Masha? Now, starting from this one, if the distance from the top of a wave to the bottom is, let's say this distance that we have, it is, you call that 18 centimeter. Masha? What is the amplitude of this wave? We said amplitude, it is either up or down to the maximum. Yeah? If the whole thing from the top to the bottom is 18, what is the amplitude? Isn't amplitude half of that? Yes, so 18 divided by 2, so the amplitude now it is going to be 9 centimeter. If this is in centimeter, very, very good. Now there's one more thing as well, Basha. Now we've learned about the amplitude. Let me erase this one here. Starting from this point to this point here, let's say this is 10 centimeter. Basha, what is the wavelength of this wave? So Baba Goodman, wavelength, no matter where you start to the same exact point, that'll be one full wavelength. Starting from a crest to another crest, that'll be one full wavelength. Yes or no? But what you see here, Baba, we can say the distance from a crest to a trough, isn't that half of that distance here? Right? Isn't that half of that distance? Yes, it is. So if the half of a wavelength is 10, so what do you think a full wavelength would be? You could just multiply by 2. That is going to be, so one full wavelength, that is going to be 20 centimeter. Basha? If not, you could say half a wavelength if you prefer an equation. If half a wavelength, I get half a wavelength equal to 10 centimeter, the one wave kamil and you could multiply both side by 2 or cross multiply. So the wavelength is going to be 2 times 10, which is going to be 20 centimeter here. So this is how you can do that, Basha. So easy peasy. So let's not forget the distance between crest to crest, trough to trough, it is one full wavelength. But if it is from a crest to a trough, that'll be only half a wavelength. So I sometimes also challenge my students as well. Sometimes I'll give them, for example, questions like this. Watch this. The distance from, or starting from this point here, or maybe let's just start from this one here. Okay, the distance from this point, so we could have started from the other one actually, it doesn't matter. The distance from this point all the way to this point, watch this. All the way to this point is, let's say, okay, you give me a number. Let's say 12 centimeter. Basha, what is one full wavelength? Now, this is also very easy, Baba. Watch this. Now, the easiest thing, if this is not the one full wavelength one, yeah, you can always split a wavelength into 4 quarters in here. How many quarters? 4. That'll be 1, and this is 2. So every wave, you can see that it consists of 4 quarters. 1, 2, 3 quarter, and 4 quarter in here. Now, take a look. How many quarters do we have? Up to this point, that is 1, 2, this is 3 quarter. If I have another quarter, that would have been 1 full wavelength. But the distance from this point all the way to this point, if it is 12 centimeter, so what is the length of one full wave? There's also something else actually. So now we can say 3 quarter, 3 over 4 of a wave, it is equal to 12 centimeter. Now you can cross multiply. All right, so wavelength dakata, 4 times 12, divide by 2, divide by 3. In this case, of course, we can say it is equal to what? You could just simplify in this case, it is equal to 16 centimeter. That would be the one full wavelength. If it is given, or the choices are given in centimeter, you can keep it. If not, you can convert to meter, which is going to be 0.16 meter. Basha, there is another way as well. If the distance up to this point is 12, and these are 3 sections, yeah? Now we know that if this is 12, yani each one of these section it is 4 and 4 and 4 one, yeah? Basha. If each section, not section, if each quarter is 4, then of course the other quarter is going to be 4 as well. So that is 8 and that is 8. So the total here, it is going to be 16, and that is going to be the length, or one full wavelength. This is another way you could do that mentally without needing any calculation. Of course, you need to know more, or maybe we can say with practice, of course, you'll get way better in solving these questions, and of course, faster too. Now, remember, there is also one thing I forgot regarding this transverse wave in here. Okay, once we're doing this normally, there is always written displacement here. Okay, didn't we say the amplitude would be maximum displacement up or down? So this side here, or the y-axis, represents the displacement of the particle, like how far they are displaced from their equilibrium position. This will be y positive, and this is going to be y negative. But when it comes to displacement, we always use the square root of the value. So if it is, let's say 5 centimeter up, that is, we'll just say 5. And then of course, this is going to be 5 centimeter down as well. These numbers, we don't normally mention positive or negative. We'll just say the amplitude is 5, and that'll be it. Whether centimeter, meter, depends on what is given here. So once again, this is the maximum, the highest point on a transverse wave, it is called crest. The lowest point, that is called trough. The distance from one crest to another, or from one trough to another, that is called wavelength. And amplitude was, it is the maximum displacement from the equilibrium position, either up or down. These are the definition one more time. Crest is the highest point, just remember the keywords. While trough, it is the lowest point, Asha, below the equilibrium. Amplitude, we said, is maximum displacement from the equilibrium. Excuse you. Excuse me. And then don't forget, we can also say amplitude, it is crest or trough distance. So don't confuse between these two. We cannot say crest would be the amplitude, no. So we said this is crest and this trough. If you say crest distance, like how far the crest is, then that'll be the displacement, Basha. And then, or how far the trough is, that'll be the amplitude. Don't forget. Now you might say, Mr., what is the difference between crest and amplitude, Basha? But when we say crest, that is just a name that we give to the maximum point, or the not maximum, to the highest point on a wave. But when we say the highest point on a wave, like we don't necessarily tell you how high it is, Basha, but that'll be just the peak of a transverse wave, Basha, that'll be crest. But if it is amplitude, you have to mention how much it is from the equilibrium, Basha. So we can say crest and trough, these are points, okay? Like how high or how low they are. The top of a wave, the bottom of a wave, these are crest and trough. But if you're saying amplitude, you actually have to measure how far is it from the equilibrium. That'll be the difference between crest, trough, and amplitude there. And then the last thing that we have is the wavelength. We said it is the distance between two adjacent similar points on a wave that have the same speed and direction as well. Now, I think it is time to talk about longitudinal waves. Yalla Baba, what are longitudinal waves? Longitudinal waves, we can say these are waves whose particle vibrate parallel to the direction of wave travel. Let me draw a transverse wave for you, but then we can use a spring to draw a transverse wave. So take a look, here's a spring. So at some points, the springs are closer to one another. Some other points, these are far from one another. Again, closer, and then far from one another, Basha. So again, closer. So this is, we can call this one a longitudinal wave in here. If we use a spring, we call this region of a spring, we call it compression. What do we call it? Compression. Why do we call it compression? Because the particles are where the spring is coiled up, compressed, pressed together. And this region here, it is not compressed, it is extended, or we call them stretched. Basha. Compressed, just say it doesn't matter. Let's just call it compression here, and we call this one stretch in here. One more time, compression, and then stretch again. But if we take the motion of one particle here, this particle, this is, or if we take a particle maybe here, this particle is going to move this much forward, and then after that, it's going to go back in here, and then backward in here. So we can see that the particles in a longitudinal wave can only vibrate forward and backward, and that is parallel to the direction of wave travel. That would be the key difference between transverse, Basha. But by the transverse, the particles are moving up and down, Basha, at a right angle to the direction of wave travel. But later, the particles are moving parallel to the direction of wave travel. All right. And then, of course, later on, we'll use, for example, sound as well. So longitudinal wave sound would be one example of that. And if we use sound instead of this one here, this is in this region that we have compression, there will be a lot of air particles there. Asha, a lot of air particle. Now that is, of course, it is called compression here. Right, let's do one more actually. So this region here, that'll be rarefaction, where the particles are far from one another, or you can see that the density of the particle is less compared to the other region here. Okay, so this is going to be something like this, and it continues, of course, like this one too here. So now, for when it comes to this region, now, again, it is also called, if it is sound particle, it is called compression. What is it called? Compression. What about this region? Now, if we're using air particles for sound here, we call this one rarefaction. Rasha, so compression, it is a region where the air particles are closest. Here, the same where the spring coils closest, Basha. All right, rarefaction, it is a region on a wave where the air particles are far from one another, or we have the least air particles there. So compression and rarefaction there. Don't forget. Okay, now sometimes, because you can see that the air particles are very close to one another, good man, if there are a lot of air particles there, of course, we can call this one a region of maximum what? Maximum pressure. Rasha? Pressure, or sometimes you can call it maximum density too. What exactly, or why exactly do you call it maximum pressure? We know that the more the particles, the more they kind of like collide with one another, so they apply a force on their surrounding, right? So this is where maximum pressure comes from. What about maximum density? Right, it's just like the density of, or population density. The closer the particles are from one another, we can say the density of the particle is maximum. So this region, you can also call that, we can call this one maximum pressure or density, and then we can call this one the opposite of that, which is going to be minimum what? Minimum pressure, or you can say minimum density. All right, so this is regarding a longitudinal wave. Asha, we can use a spring. This region where the coil is closer, we call it compression, and this is stretch. But if we use sound waves, right, this is called compression, and this is called rarefaction here. All right, and then if we take the motion of one particle here, this particle would only vibrate back and forth, which is parallel to the direction of wave travel. This is how the wave travel, and this would be the direction of the air, or this particle vibration, and you can see that these two are parallel to one another. Don't forget, longitudinal waves need a medium to travel through. Without a medium, they cannot travel through. Basha? So this is another point that you need to be aware of, this one too. All right, so longitudinal wave, it is a wave whose particle vibrate parallel to the direction of wave travel. Don't forget this keyword. The particles are, that'll be for longitudinal, parallel to the direction of wave travel. And then again, in longitudinal waves, that'll be the properties, but when the particles vibrate parallel, and then longitudinal waves, all of them need a medium to travel through. Without a medium, they cannot travel through. And this would be a spring here. Obviously, this region is called compressed, that'll be stretch. You can see that these are, or this point is closer, this region kind of like stretch, all right? Again, compressed and then stretched. So this is how it can continue. Now, the next thing that we need to know is this one here. This diagram that we drew, All right, let's go back to the whiteboard. This diagram that we drew earlier here, we can convert, Basha, this longitudinal wave to a sine wave. What do you mean by a sine wave? Now, don't forget, if I want to do that using the spring or this one here, if I want to convert this one to a sine wave, don't forget, this is how it is going to be. Every region that is compression, it is going to represent what? It is going to correspond to a crest, and this is going to correspond to a trough, then another crest, and then this is how it looks like. Watch this. You might say, Mr. Isn't this a transverse wave? No. Watch this. This is called a sine wave now. Previously, we're talking about. So both transverse wave and longitudinal wave can be represented by a sine wave. So now you might wonder, so how do you differentiate between the two? Let me walk you through this one first a little, and then I'll tell you how you can differentiate between the two as well. So this region here, now we said that this region, there's maximum pressure and density, right? So that'll be maximum pressure and density corresponds to a crust, corresponds to. It is not the same. You cannot call this part a crust anymore because this wave or sine wave now it is representing a longitudinal wave. What about the region between two compression here? That'll be represents what? That is corresponding to a trough. Again, corresponds to a crust, maximum pressure and density, and then there. So how do you differentiate between this and a transverse wave? Watch this. If we're going to convert longitudinal waves or sound, let's say whether if it is a spring or sound wave, into spring, longitudinal, or a sound wave into a sine wave, at the y-axis here, you have to write this as density or pressure. Density, or you can write pressure here, right? So it could be both together. So if it is going up, so this region here, of course, it is going to be maximum pressure and density. It's one of them. What about this region here? It is going to be minimum pressure, or it could be density. Al-Muhim, if you ever given a wave like this, a sine wave like this, and it is written pressure or density, that wave immediately represents a longitudinal wave. You can never call these regions now crust or trough. No, we'll say this, the top of a wave represents the center of a compression. The center of what? Of a compression. What about this part here? It represents the center of a rarefaction. So once again, we'll say the center of a compression here, it corresponds to a crust. It's not a crust, it just corresponds to it. Yani it is kind of like substituting that. It is in the place of crust. And then the center of a rarefaction would be representing or corresponds to a trough, and then it continues like this. Basha, now going back to the other one. So if I have two waves in Wizari, Basha, one of them, all right, how do I know which wave is for which, right? Like which one is for transverse wave and which one of them is for longitudinal wave? Baba, listen, if it is written displacement here, displacement on y-axis, this wave would be for transverse wave, Basha. If it is written, like I said, pressure or density, and of course it could be written both up and down or positive, negative here, it doesn't matter. As soon as you see pressure or density, that is going to be for longitudinal waves. This is how you can separate them. And of course, we have Wizari questions. It is written density or let's say pressure here. So that wave represents a longitudinal wave. It says what wave is this? Is it longitudinal or transverse? So of course, you have to say the longitudinal, because if it is written pressure and density, that is taken from this. That would be a sine wave of a longitudinal wave. But man, again, if there's no pressure and density, when you see displacement, that is going to be for a transverse wave there. And that is something very important. You need to know this so that you can answer questions correctly. And this is exactly what we have. So the displacement, previously we've mentioned that, of the particle is parallel to the direction of wave travel. That is one, and this is the other one as well. So whenever you see a wave like this, but instead of displacement it is written pressure and density, this wave corresponds or it is a longitudinal wave. So whether you do that here or there, doesn't matter. And you can see that the center of compression represents or corresponds to a crest. Center of a rarefaction represents a trough in here, and this is how it is going. And you can see that this one surrounding air pressure, you could say density, this would be the highest, this would be the lowest. Al-Muhim, you see pressure and density at the y-axis. That is immediately, we can see that is going to be representing a longitudinal wave. And you can see the crest where the Cyprian coils are compressed. These are regions of high density and pressure. Conversely, the trough, these are, or you can say where coils are stretched, these are regions of low density and pressure. Now there's also another question, says, what is common to all waves? Now we know that all waves are, we can see that the motion of a disturbance, right? Without, or you can say if there's no disturbance, there will be no waves at all. So that'll be one thing that is common for all waves that we have. Basha? Another question that we have says, how do transverse and longitudinal wave differ? Well, just knowing their definition would be the difference between the two. Gutmann, transverse waves are waves whose particle vibrate at a right angle to the direction of wave motion, or perpendicular. While longitudinal are waves whose particle vibrate or oscillate, doesn't matter, at a parallel to the direction of wave travel. That'll be the whole thing as an answer to this question. Here, the figure below depicts. What does depicts mean? It means shows or resembles. When a pulse wave, remember, it's just a pulse wave traveling on a spring here. So just because it is a spring, that doesn't mean it is always longitudinal. No. I mean, a spring, if it curls back and forth, that is longitudinal. But if it is moving up or down, you're moving that spring up and down like a rope, of course, that can be used as a transverse wave as well. Only the shape would be a transverse wave. That's the purpose in here. Okay, now, so the question says, in which direction are the particles of the medium vibrating? Well, if you look at this one here, it is just a single pulse, right? So if it is a single pulse, and this is how you see, if a particle is here, how do you think this particle is vibrating? Is it up, down? Is it just up or just down, or is both up and down here? So because it is a pulse, don't forget, and this pulse is just shown upward here, so we'll say the particles of the medium at this picture or diagram that is shown here, it is only vibrating up here. Basha, that'll be the answer to the question here. So we can say upward, and can I also say this is perpendicular to the direction of wave travel? Yes, so we'll say the particles are vibrating upward, which is perpendicular to the direction of wave travel, so it is only vibrating up. Okay, next, says, is this wave transverse or longitudinal? Basha Gutmann, in transverse, the particles are what? The particles are vibrating up or down which is at a right angle. But for transverse, Gutmann, for longitudinal, the particles would be vibrating parallel to the direction of wave travel. Esta, which one is this? Is it vibrating at a right angle or vibrating parallel? Obviously a right angle, which makes it a transverse wave here. Okay, the next question that we have, it says what? It says, in a stretched spring, so there's a spring that is stretched, Basha, several coils are pinched together and others are spread further apart than usual. What sort of wave is this? Let me draw the diagram for you. Gutmann, some regions, the coils are pinched together, very close together, and some other regions are spread apart. And then again, pinched together and then spread apart. What kind of wave is this? Of course, you already know the answer. That is going to be a longitudinal waves. Okay, the next part of the question says what? Why do sound waves need a medium through which to travel? Well, you have to think about this question for a second. Why do sound waves need a medium to travel through? Well, first of all, let me tell you something. Sound waves are caused by vibration. So watch this, for example. If we do this now, once you struck something or hit something, then you're basically making something vibrate, right? So when this thing that vibrates, you can call it a source one, That vibration, of course, now it is going to be in contact with the surrounding air. It makes the air that is surrounding the object to vibrate with it, right? Now this vibration will be passed on from one air molecule or particle to another. This is how it can be traveled. So now let's go back to the question. Why sound waves need a particle to travel through? We can say sound waves need a medium to begin with, let's say, to start the sound first. If there's nothing or no particle to make it vibrate, will there be any sound in the first place? No. That is the first part. Put that aside. Now the next part. Now after the sound is generated or produced, now of course in order for the sound to move from, let's say, one place to another, we need these particles to be able to transfer the energy. Without a particle, it cannot go. So of course, if you ever got a question, can sound travel through empty space? Of course, the answer is not, because there's no particle there. Or we can say in empty space, sound cannot travel, because sound is a mechanical and it needs particles in order to travel. So once again, sound waves are caused by vibrating particles in the first place, to produce the sound. Without particles, there will be no sound. There will be no sound, of course, to transfer. And these are some Mosaic questions, and let's give it a try in these questions too. These are pretty easy actually, but make sure you leave none of these questions. Make sure you solve them all. It says the region of a longitudinal. You have to underline this, Basha, in which the pressure is at maximum. What is at maximum? Pressure. Basha Gutman, what do we call the region where the pressure is maximum, right? And it is longitudinal. So if you're given crust and trough, you cancel those immediately, Basha. So you can see here, crust and trough, these are not part of a longitudinal. So it is either, now you got 50% chances. It's either rarefaction or compression, Basha. Where the pressure is maximum, that is compression. All right, it is a type of wave, that'll be second, a type of wave that makes particle of the medium to vibrate, Basha. How vibrate? Parallel to the direction of wave travel, Basha. Which one of these sounds we've studied, the particles of the medium vibrate parallel? Yalla kaka. Manchant particle كيف parallel. It is a longitudinal wave. At the transverse, good man, the transverse, the particles vibrating at right angle. Transverse. What about light wave that is also transverse? Is incorrect. Electromagnetic is also transverse. Question 3 says, which one of the following is not a mechanical wave? Remember I told you to memorize all the electromagnetic waves. Of course, for a question like this, says which one of them is not a mechanical? In other words, sometimes they can change this one. They might say which one of them does not need a medium? Is it not the same thing? Yes. So not a mechanical. Is visible light a mechanical wave? No, it is electromagnetic waves. Basha Kota, this is not a mechanical. All right. What about a wave on a vibrating string? Because there is a string here, so this is a mechanical. What about sound? It is also longitudinal. It is a mechanical. It needs a medium. What about water waves? It is also a mechanical wave. Let's explain this in a different way. Man, only visible light does not need the particles of a medium. In order for, or the waves on a string, if there's no string, can you even, for example, will there be any sound at all? No. Okay? So as long as there is a string, that means you need a particle or particle of the medium so that it can travel. And you know that sound, of course, is caused by vibration, so it needs the particle again. And water waves, you already know that. Without water, there would be no waves here. All right, what about this question here? 4. It's easy, but of course you need to do that. It says if the distance between two successive crests in a wave is 20 centimeter, find its wavelength. Now you have to be careful about it. So this is, let's say, a transverse wave. So the question tells you the distance between two successive crests. Let's just write the nicer wave here. So here, this is a transverse wave here. And this is called crest, and this is a crest. The distance between two successive crests, it is 20 centimeter. Baba, I got baby. 20 centimeter. Find its wavelength. Isn't the distance from one crest to another, isn't that one full wavelength? Yes. But if you've noticed, this one is given in centimeter, and the choices are in meter. So don't, all right, do not make any mistakes in here. They convert centimeter. So the wavelength now it is 20 centimeter. But now you have to convert to meter. So divide by 100, that is going to be 0.2 meter here. And of course, that is, we can say the wavelength in meter. I believe that is going to be the end for this session. Next time, inshallah, we're going to start with period, frequency, and wave speed. That is also very interesting. So till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.